Hi. In the previous podcast, we explained to you very shortly the basic principles allowing to model water transport in the soil as a basic of soil process modeling. We can summarize what we have learned in this previous podcast with the 4x2 summary. To develop our transport equations, we used or considered two physical principles: the mass conservation, obviously, and the Darcy flow principle. When combining the mathematical expressions of these two physical principles, we obtain two equivalent second-order nonlinear differential equations allowing to describe the water transport in soil. If we express the water flow in terms of water content, we refer to the Fokker-Planck equation. If we express the water flow in terms of the negative suction head, we refer to the Richter's equations. These equations are the so-called governing transport equations for describing water flow in unsaturated soil. To be able to implement these equations, we consider two fundamental characteristics: the soil water retention curve and the soil hydraulic conductivity curve. Both characteristics constitute the basic soil hydraulic functions. They relate theta, water content, to H, suction head, and K, hydraulic conductivity. They are soil specific and constitute as such the hydraulic signature of a given soil. And from these basic hydraulic functions, we obtained or derived auxiliary functions that are included in the governing transport equations. These are the differential water capacity, defined as the slope of the water retention curve, and the hydraulic diffusivity, defined as the ratio between the hydraulic conductivity and the capacity. For being able to solve now the transport equation, which means to integrate the governing equation in space and time, and hence to obtain continuous descriptions of either water content or suction head as a function of space and time, we need to know the basic hydraulic functions. The modeling of soil hydraulic processes, this is achieved by modeling the soil-specific functions, nonlinear soil hydraulic functions, with parametric models. And that can to some extent also be based on physical principles. An example for such a model for the soil moisture retention curve is shown in this present slide. In a very simplified way, we can consider that the soil will remain saturated until a critical suction head is reached. This actually suggests that we will need to apply a minimum critical suction head before the largest pore in the soil will be drained. If the absolute value of the suction head is smaller than this critical value, Hi, hence when it is less negative, the soil will retain all its water. Once the critical head is reached, corresponding to Hi, the soil will drain. First the larger pores, and then of course the smaller pores, until a minimum water content, theta r, residual water content, is reached. This level, even if we apply more suction, the water will no longer be drained from the soil. Given the irregular distribution of pores in a porous medium, we may consider that the relation between water content and suction head will be nonlinear, in particular when the critical suction head Hi has been reached. Such process can now easily be modeled by a parametric equation. This parametric equation has already been proposed by Brooks and Corey in the 60s. The mathematical translation of the previous physical consideration is given in these two equations, referred to as the famous Brooks and Corey model. With the Brooks and Corey model, we are able to parameterize the nonlinear retention curve with four parameters: saturated water content, theta S. This corresponds nearly to the soil porosity. The residual water content, theta R. Hi, the critical suction head, and lambda, the slope of the retention curve. This parametric retention model is very convenient as we can predict the water content in terms of suction head and vice versa. Yet this model has also a disadvantage and a problem. It is actually discontinuous in a mathematical sense at the air entry value. And hence, at this place, the differential water capacity does not exist. And this complicates, of course, the solution of the Richards equation, which implies that we need to define the differential water capacity everywhere. For solving this problem, a continuous parametric retention model has been proposed. This approach, no discrete threshold value is considered where water starts draining. It is considered that soil starts draining whenever a small suction head is already applied. The transposition of this concept in a mathematical form has been done by Vanclooster in the 80s. He proposed a parametric equation based on 5 parameters, the so-called Vanclooster retention model. Consider saturated water content, theta S, residual water content, theta R, alpha, a parameter related to the inverse of the air entry value, N, a slope parameter, and M, a parameter that determines the asymmetry of the curve. With these parametric functions, we can actually now model the retention curve for any soil on the world, for any soil sample collected somewhere in the world. And as already stated in the previous podcast, this retention function will be strongly impacted by the soil texture. The second function that we need to define for solving the transport equation is the soil hydraulic conductivity function. And also this function is strongly nonlinear. Strongly nonlinear in terms of soil water content and hence also in terms of soil suction head. But in contrast to the water retention curve, the unsaturated hydraulic conductivity curve is much more difficult to measure. Actually, where the soil water retention is mainly determined by soil textural properties, the soil hydraulic conductivity is determined by texture and soil structure. And soil structure is not easy to assess and variable in time. In this figure, for instance, an example is given of the assessment of the hydraulic conductivity function of a loamy soil in Belgium. We can see that for this soil, the soil hydraulic conductivity drops with 3 to 4 order of magnitudes when the soil gets dry. Also, for the hydraulic conductivity functions, parametric models have been proposed and developed. Some popular models are given in this slide. And some models are even linked directly to the retention model, like for instance the Brooks and Corrie. They are based on a combination of a pore size distribution model, the water retention model, and a capillary percolation model. As such, there is a consistency that has been created between the parameterization of the retention and some parameters used in the hydraulic conductivity function. This model, for instance, an additional parameter has been added, Ks, which is the saturated hydraulic conductivity. With these expressions, we are now able to model the soil hydraulic functions. If we have parametric models for the basic functions, we easily can define parametric models for the auxiliary functions. We propose to discover in the upcoming Python notebooks some descriptions and some exercises related to the parameterization of these hydraulic functions.